Everybody. So in this example here, we're going to figure out how to graph a piecewise function. Um, so in the beginning, before I think they cover a graphing piecewise function, you kind of want to understand how you plug in x values and how you figure out the output, okay? So let's do that real quick. So let's say I wanted to plug in, 3, the x value 3 into my function here. The way you read this is you're gonna think of it as like you're gonna use two functions, but these conditions tell you what must be met for that particular x value. So if I plug in an x value that's greater than or equal to 1, I'm going to use this linear function. But if I plug in an x value strictly less than 1, I'm going to use this linear function. And because 3 is greater than or equal to 1, I'm going to be plugging 3 into this linear function here. So that means that I'm going to do 1 plus 3, which gives me 4, since I know that 3 is greater than or equal to 1. Okay? So that means that when you plug in 3, we output 4. Now, if I plug in something like 0, since 0 is strictly less than 1, I'm going to be using this linear function instead of the bottom one. So that means I'm going to be plugging in 0 into the top linear function. So it's 2 times 0 minus 1. And then that's going to give me, what is that? 0 minus 1, which is negative 1, since 0 is strictly less than 1. Okay? So it's like a little program. You plug in an x value, you check the condition, and you say, does it satisfy this condition? No. Does it satisfy this condition? Yes. So I'm going to use this function. Okay? So in terms of graphing, imagine you're being asked to graph both of these linear functions, but you are only going to really graph this part of the graph will only correspond to x values greater than or equal to 1, and this part of the graph will only correspond to x values strictly less than 1. So let's see how we would do that. Let me use this color here, a little more friendly. So let's say we want to do the top one, right? So if I want to look at, let's say, if x is less than 1, that means my function is only going to be using the top value, the top linear function. So that's 2x minus 1. And then since this is a linear function, we want to break down its components. So this is the slope. Here m will equal 2, but to write it as a fraction, 2 can be rewritten as 2 over 1. That way I know my rise is 2 and my run is 1. And this constant value will be the y-intercept. So that will be b equaling negative 1. So that tells me where to start in my graph. So if I wanted to graph this one here, I'm going to start at my y-intercept, which is negative 1, which is right here. And my slope says go up 2, so 1, 2 over 1. And I'm going to keep doing that. And then up 2 over 1. So I would keep doing that. But now when you're going to graph it, right? Like normally you would just graph it and connect the dots like this, connect the points, right? But when you're graphing it in this case, you want to graph it only for x values that are strictly less than 1. So here's the x value 1. So I'm not going to include anything greater than or at 1. So notice that at 1, there's going to be an open circle since this function does not include 1 as part of its input values. So the graph really is only going to be graphed for x values that are strictly less than 1. Let's see if I can do it. There we go. Okay. Normally, like I said, you would graph the entire line, but because this is a piecewise function, I only graph my graph using the x values that are strictly less than 1. So if I want to graph the other one now for x values greater than or equal to 1, let me do that in a different color. Let's do something a little different, lighter green. So if x is greater than or equal to 1, Now my function is going to only be using the bottom linear function, 1 plus x. And so since this is a linear function, you can write it like this for if you want, or I think some people like to see it in the mx plus b form. So I'll just switch it. Same thing, just depends on your style. So here, notice that the coefficient in front of x is 1, and that is what our slope is for this linear function. So your slope here, m equals 1, but to write it as a fraction, that's 1 over 1. And then here, your y-intercept is going to be b equals 1. So that means that when we graph this function, this part of the function, we're going to be using these properties of this linear function, but only graphing it for x values 1 or greater. So I'm going to use my green marker here, and let's graph it like normally, right? Let's pretend that it wasn't a part of a piecewise function. So if this was just a normal function that just equaled 1 plus x all through, I would start at my y-intercept 1, which is right here. And then my slope says go up 1 over 1, so up 1 over 1, up 1 over 1. So up 1 over 1, up 1 over 1, up 1 over 1. Now here, though, we are only going to graph it for x values greater than or equal to 1. So I don't want to use anything that's less than 1, right? So I'm going to exclude this x value. And do I do an open circle or a closed circle at 1? Well, because you have equality, 1 is part of an input value here, so I'm going to leave it as a closed dot, okay, a closed point. Versus in the other one, positive 1 was not part of my input values for this part of the piecewise function, which is why I have an open circle. So because 1 is included, it's going to be closed, and then I connect it using my slope here, and then this would be the other part of the graph. Now, I need you guys to understand that this is not two different functions, or two different, it's not graphs of two different functions. This is both pieces of this is the graph of this function. It's just broken down in a different way, okay? But in this case, this is all the graph of one function. In this case, it's a piecewise function. So if you were to ask to find the domain of this piecewise function, you wouldn't do it separately. You would actually consider both of these parts of the graph as being the same for the same function. So you would look for x values. Notice here the domain, there is no smallest x value. Let's do it just for fun. So if you were to being asked to find the domain, there is no smallest x value here. So I would put negative infinity. And then you would say, okay, what about these x values? Yep. And then at 1, you would say, oh, 1 is not included in my function. But because the green part of the graph is also a graph of my function, notice that even though 1 is not included in the blue part, it is included in the green part of the graph. So 1 is an input into this function, right? Notice that if I plugged it in, it goes into this part of the function. So it is an input. So I'm not going to exclude 1. It is actually an input. So in reality, I'm still going to keep going. There is really no break at 1 because it is an input value. So I keep going, and there is no greatest x value. So I would say there is no greatest input value, and it goes up to infinity. If you wanted to do range, you would say, okay, let's look at the y values. Is there a smallest y value that's part of my graph? Nope, because the arrow says this keeps going down forever. So there is no smallest y value. That's an output. And then I keep going and I say, okay, what about when we get to this little weird break here? 1 is not, notice that there is no part of either the blue or green part of the graphs that uses 1 as a y value for a point. So 1, the y value 1 is not an output value. So it is not in my range. So we're going to exclude 1. We're going to say 1 excluded, but because there's more to the graph of the function, I need to keep going. So notice that 1 is not included, and anything in between 1 and 2, those y values are not part of the graph. Up to 2, then I start again. So the way you say that is you're going to exclude 1, then you're going to union, and then anything between after 1 and between 1 and 2 is not part of it. But then once I'm at the y value 2, I start getting y values that are in my range. So I'm going to go start at 2 again, but 2 is included, so I put a square bracket. So remember that the union is used to kind of like group up the intervals together. And then I say, okay, and then there's no biggest y value after that. So I'm going to write up to positive infinity, like this. And remember, you never include infinity. So that would be the domain and range of this function. So even though it has two parts of, like two separate graphs, it's really just one big graph of one function. All right? Thank you.